Now, we've already looked at the elimination of halogenoalkanes using hot ethanolic sodium hydroxide. In this video, we'll look at the elimination of alcohols, going through the overall reaction and the mechanism. I'm going to actually show you two versions of the mechanism, the more detailed version of the mechanism so you can actually understand what's going on, and then the simplified version of the mechanism that might just save you some time in your exams. So let's go through the basics. I'm going to go through these pretty quickly because we spoke about it for halogenoalkanes, but essentially elimination, we know we're going to remove a group, and so we are going to produce an alkene. Right, so from an alcohol to an alkene, we will need to use an elimination mechanism. Now, the reason I just corrected myself there, okay, let's say I did it on purpose, is because the name of the mechanism is elimination, but the name of the reaction is often called a dehydration reaction. Right, so dehydration reaction, but elimination mechanism. The reason it's called dehydration, well, if you think if you're dehydrated, you don't have enough what? Water. So we dehydrate an alcohol by removing the water, which is what produces our alkene. So our general equation would be an alcohol, and that's going to give us an alkene plus water. Okay, you might think, how do we do that? What do we use? Our reagent that we use is a concentrated acid. So I'm going to put H plus over the arrow, and that's because this is actually a catalyst. It's going to be used in the beginning, but it's going to be regenerated by the end of the reaction. So it hasn't actually been used up. It's just speeding the reaction up. Now, where does that H plus come from rather? This can be from concentrated phosphoric acid or from concentrated sulfuric acid. Okay, this is the one that I'm going to be focusing on in this video because it's the one I'll use in the mechanism, but either will work because ultimately what do we actually care about? It's the H plus. So let's go through the mechanism. I'm going to choose, oh gosh, which alcohol should we choose? Let's say propan 2-ol is a decent one. I'm just going to shuffle over to make sure that there's enough space. Hopefully you can still see me, but if you can't, I mean, doesn't really matter. It's the chemistry that does matter. So we've got our alcohol. This is going to be acid catalyzed. So in our first step, I'm using sulfuric acid, and I'm going to draw the structure of sulfuric acid. So that's going to be an H attached to an O, attached to an S, and then that's attached to the rest of it, which I don't really care about as much. I'm going to write that as O2OH. So the very first thing that's going to happen is we have got a polar bond in the in the sulfuric acid, making this H partially positive and this oxygen partially negative. We also have a lone pair on the OH of the alcohol group, the hydroxy group. And so our first curly arrow is the lone pair attacking that H and then breaking this OH or HO bond. And that gives us a protonated alcohol, where instead of just OH, it's now OH2 or H2O, same. And this has got a positive charge because it's gained that H plus from the acid. Oh, that shouldn't be an O. Wow. Okay. Now for our next step, this is OH2 or H2O, it's water. So really that can just fall off. So I'm just going to put that in green so we can see it really clearly. So for our next curly arrow, all that's happening is that CO bond is breaking, causing the water to just fall off. So curly arrow from the middle of there onto the oxygen. Now what do we have? We have something that should look familiar from your electrophilic addition mechanism, which is a positively charged carbon, which of course we call, go and say it with me, I can't hear you. Okay. A carbocation intermediate, right? Because both of the electrons from this bond have gone to the water. So that carbon has actually lost an electron technically. And then plus H2O over to the side. Now, how do we get from this over to our alkene? Well, let's not forget, we've got this bit here that came from our original acid. So we've got OSO2OH that now has a lone pair and a negative charge from having lost that H earlier on. So what can that do? Very similar. This is where we have to start linking our ideas. Very similar to our elimination of halogenoalkanes mechanism. This is essentially going to act now as a base, and it's going to accept an H plus on either from an H on either adjacent carbon to that carbocation. Now, for this particular example, this is symmetrical, which means that these two carbons and therefore these hydrogens are exactly the same. So it doesn't really matter in this example which hydrogen we take. I'm just going to take the one that's closest to it. So from the curly arrow to an H, so accepting that H plus, and just like before, that's going to cause this CH bond to break, forming a carbon-carbon double bond. So what do we finally end up with? We formed a carbon-carbon double bond between carbons 1 and 2, and we've lost this H, leaving just two H's on the one on the left, one H in the middle, and then the original three H's on the right. And because this OSO2OH, right, the sulfuric acid, the sulfonate ion that has accepted this H, that has regenerated our sulfuric acid. So now we've got back our, I'll write it exactly like this, just so we can see it super clearly. We have regenerated our sulfuric acid. That's what this is, H2SO4. And that's what this is, H2SO4. So we can see it's just acted as a catalyst. It has allowed our reaction to take place, right, faster than it would without it, but it has not been used up itself. It's been regenerated by the end. Now, as promised, I said I would show you the overall mechanism so you can really see what's going on and how the acid is catalyzing this reaction. But I did say I will show you a simpler version that you can use in your exams if you don't necessarily want to write out this whole acid part. And as opposed to writing this all out again, I'm just going to get rid of the bits that you don't necessarily have to show. So instead of showing the whole sulfuric acid, what you may have noticed already is the only part that's actually important, that's actually kind of joining in with the mechanism, is the H plus. So instead of having it as the whole H2SO4 and spreading it out with the structure, instead, I'm just going to include the H plus ion, right? Because that's what the OH is accepting to give us this OH2 plus or H2O plus. Then, just like before, our water falls off, giving us our carbocation intermediate. And then to show our carbon-carbon double bond forming, instead of showing the ion, the negative ion accepting this H, we can just show the CH bond breaking, forming the carbon-carbon double bond and giving us our final product. And instead of giving us back sulfuric acid, H2SO4, I hope you can see that. I'll write it up here in case you couldn't. Instead of reforming H2SO4, we can just show it reforming, I'll do it here. We can just show it reforming H plus because this H has fallen off and that is now that. I was going to say nice and straightforward. I don't want to lie to you, okay? This is one of those mechanisms, just like the elimination of halogenoalkanes, that is not quite as intuitive as some of the others, right? Most of your other mechanisms, it's just opposites attract. So obviously the curly arrows go from X to Y. For this one, you do have to spend a little bit more time learning the steps, understanding what's happening in those steps so that you can draw out the mechanism for the elimination of any alcohol that you may come across. Just like your halogenoalkane elimination, you can get some isomerism for this because if this was not symmetrical, then taking either of these two hydrogens would give us different products. And Because we're producing an alkene, we would also want to look out for if there were EZ isomerism. Now, I spoke about that in more detail in the elimination of halogenoalkanes video, so I would recommend, it's the same principle when it comes to the isomerism, that you go back there and watch the end of that video for those examples and any other isomerism videos that pop up on my channel in the future. So make sure that you have subscribed, make sure you've liked the video, leave a comment if you've got any questions, or if you just want to say hi, and I will see you in the next one.